Today I'll be talking about measuring your applications in production. My name is Jason Keene. I work at Pivotal Software. I work on observability problems for Kubernetes and Cloud Foundry. I've worked on Cloud Foundry for about a year and a half, and it's been about a year and a half-ish for Kubernetes. So today I want to talk about measuring your applications in the production environments that they're running in. And the reason I wanted to talk to you about this is I feel it's invaluable from a development perspective to be able to do this. Oftentimes, I feel the developers don't have the tools to be able to ask the questions they want to ask. So I feel this is something that can provide a lot of value to developers. So why would we bother measuring in production? There's a bunch of different reasons why you might want to make direct observations of your production environment. One of them is, you get to see your software under actual load. So you get to see its failures when it's under load. You get to see faults as they occur. You can discover patterns of usage of your users, which can inform future features. But primarily, you really want to be able to make measurements in production to be able to debug your system when problems occur. Sometimes reproducing the problem in your production environment, reproducing that in an artificial environment is too time-consuming or too difficult. And sometimes simply being able to reproduce a problem is not something you know how to do. So you have to collect data from your production environment just to seed analysis in a different environment. Ultimately, production is reality. Everything else is at best a proximity. So we need to be able to measure in production to be able to debug problems as they're occurring. But more importantly, I feel understanding the character of your workloads is critical to their successful operation. So being able to make measurements in production allows you to have an understanding of your workloads. This was discussed by Brian Cantrell a couple years ago at his 2017 GoTo talk. He said, debugging is not merely the act of making bugs go away, it is the act of understanding and gaining new knowledge about the way the system works. I think there's a lot of truth to that. So we want to be able to solve problems and we want to be able to understand our systems. So today's talk is split into 3 different sections. First, I'm going to go over a method that I like to keep in mind when I'm debugging issues. I think it's incredibly valuable, so I wanted to share that with you today. Next, we're going to go into some tools. There's been some recent developments in the past few years in the Linux kernel and some user space tools that have recently been released that I kind of want to get the word out about. So we're going to discuss some tools, and then I'll show you how to put these tools and this method into practice and applying it to a Kubernetes cluster. So let's start off with the method. So the method I like to call ask questions, get answers. So you start off, say you have a problem in front of you, start off with a space of possible causes just visualized as an area. And the function of a question is to put pressure on the area, to divide it into different sections. So in this case, our question, if it's true, the results in the category A will remain. If it's false, the possibilities in category B will remain. And then oftentimes, asking a question might not differentiate between certain possibilities, so you might have an area in between where there's overlap where you, either result of the question, that area will remain. So the function of the answer is to cut off and eliminate sections of the possibility space. And that reduces your possibility space by that amount. And so you iterate. You ask another question, get another answer, eliminate part of the possibility space. Do that multiple times until your possibility space is extremely small and you've narrowed in on the cause of your problem. So I've used this technique a lot in my career, and I find it to be very valuable. When you're using this method, it's critical that you're confident in your answers, and I'll demonstrate why. So say you ask a question and you get an answer back that you're 85% confident in the result. So you might say, well, 85% confidence, that's kind of high. But if you apply this method, it's an iterative method. So as you iterate, if you're only 85% confident in your answers, after 5 iterations, you're down to 44% confidence in your overall analysis. So what makes this even worse is after that, even if you're 100% confident in your later questions, the answers that you get to your later questions, you can't regain that uncertainty. The uncertainty has crept into your analysis, and you'll never get it back. So you really want to be extremely confident in the answers that you get to the questions that you ask. So just to kind of visualize that here, so you might think the problem is in that narrow space that you narrowed in on, but in actuality, you eliminated it in a previous step. So that's what that looks like in practice, and I can speak from experience. It's extremely frustrating when that happens. So just asking a question doesn't help if you can't get an answer to your question. Not having the right tools constrains the space of possible questions that we can ask. So I like to use the Streetlight Effect analogy here. So if you're not familiar with the Streetlight Effect, there's a story. A gentleman is looking for his wallet. He lost his wallet, and a police officer walks up to him and says, well, is the wallet under the streetlight where you're looking? And he says, no, I actually lost it in the park, but this is where the light is, so that's where I'm looking. So you might have experienced this effect in using tools and trying to debug problems yourself, where your tool kind of just illuminates a small area of possibilities, and so that's where you look. But your problem isn't, the problem isn't actually where you're looking. So what we want is a flashlight where we can walk around wherever we want and be able to shine the light on whatever we want to be able to find the wallet in the park, not under the street lamp. So we need tools that can give us answers to any arbitrary question we want to ask. So yeah, we're going to talk about some of those tools now. To start off with, I kind of just want to frame the discussion around the different types of instrumentation. So I like to view these as a hierarchy. At the top of the hierarchy is static, always-on instrumentation. These are things like logs, metrics, distributed tracing, the three pillars, so to speak, of observability. There's an incredible amount of value that you can get out of these, but the problem with these is that you're paying the performance penalty at all times. So you can't cover every aspect of your system using these techniques. The performance penalty would be too high. So they're incredibly useful. This should be the first place that you look to start debugging a problem, but they don't give you every bit of coverage that you would need. After that is static instrumentation that requires activation. So these are technologies like USDT and trace points. These are things that a developer would instrument their code with in advance. And when that code's running in production, you're not paying any performance penalty for that instrumentation. So you can kind of add more of this into your program. And then when someone wants to actually instrument your program, they can activate that instrumentation. So that gives you a little bit more coverage. And then finally, the last layer is dynamic instrumentation techniques. So these allow you to cover the broadest amount of your system. So you can use technologies like ptrace, uprobes, and kprobes to achieve dynamic instrumentation. So we want tools that can answer these arbitrary questions about our software. So we want to be able to intercept any point of execution without restarting the process. We want to be able to read from memory and registers, collect data across multiple processes and the kernel, ideally, with low overhead, and to do it all safely. So that's a tall order. So let's start with debuggers. I really like debuggers. I think they're awesome. This is actual video of someone starting GDB. So yeah, debuggers use a system call called ptrace, process trace, short for process trace. It allows a tracer program to control the execution of a tracee. So I imagine most folks are familiar with debuggers. Debuggers can intercept syscalls, signals that the tracee is receiving, can read and write to the tracee's register memory, including its text section. You can single step through the tracee, can write breakpoints. It has a lot of capabilities. One of the problems with ptrace, though, is that when the tracer is running, typically the tracee's execution is suspended. And most times that means all threads in that process are suspended. So what does that look like? So in this case, we have the tracee on the right and the tracer on the left. So tracer is just, you can just think debugger. So the tracee, there's a breakpoint set in the tracee, so that once that trap is hit, the tracee is suspended, the kernel takes over execution, and then sees that the program is being traced, will hand control over to the tracer program. Then sometime later, maybe seconds, minutes, hours later, the tracer will yield control back to the kernel via syscall, and then the kernel will then resume the tracee. So naturally, the big problem with this is suspended execution. When you're suspended, your program's doing no work, no useful work. If the tracer is slow to yield back, then this will just cripple your performance. So that's not suitable for production. Tracer is usually blocked on user input to make matters worse. So this is kind of putting the user in the loop. So user is reading from a terminal and typing into the keyboard. And so having the user in the loop adds just even more latency. So I actually used a technique that we'll discuss in a moment here where I replaced the user with a controller process. So that eliminated some of the slowness from me typing on the keyboard. So I actually used that to debug a problem that I had in a logging agent. So I mentioned I work in observability. We have an agent that runs in all of our systems, collecting logs from the system and then forwarding them out via gRPC. So looks something like this. So periodically, the agent would just stop sending any data for a matter of minutes. And then all of a sudden, it would just start resuming sending data. So this is really perplexing to us. We had these reports from people running our software, and we didn't really have any visibility into why this problem was occurring. So just a little bit of background on this problem. So the agent uses a ring buffer internally to keep track of messages. And just a little bit of background about ring buffers. You typically have a read and write indice in a ring buffer, and the write indice will always be ahead of the read indice. The read indice will not advance past the write indice. It will block until new data is available. So that's just a little bit of background that'll be relevant in a moment here. So the question that I want to ask is, when the agent is in this state, when it's not sending any data, what is the state of these read and write indices? This is just kind of a mock program that simulates the bug, so the bug that we saw in the logging agent. So I just create a ring buffer and then spin up a thread of execution to do writes and then another thread to do reads. So in this case, I'm going to instruct del, which is the Go debugger, to attach to that process. I then capture the standard in and standard out of the debugger. I tell the debugger to start, and then when the debugger attaches, it typically will suspend the program that it's tracing. So I just tell the debugger to immediately resume the tracee so that there's no performance overhead with it blocking. I then spin up a go routine to read information out of the debugger, and then I go into infinite loop, just sampling data periodically. So on the left-hand side, you can see what that sampling, the inner body of that loop looks like. So we just go to sleep for a second, and then we send a SIGINT to the debugger. That wakes the debugger up, suspends the process, and then if it's time to exit, we just tell the debugger to clean up, and if it's not time to exit, then we tell it to sample some data. And the commands that we're sending the debugger on the right-hand side here, so to sample data, we just set a breakpoint at the function that we're interested in tracing. We then continue to hit that breakpoint, and then we print out a delta between the write indice and the read indice. And then we clear our breakpoints and continue. So that's pretty much all there is to this. So I'm going to run that tracee program on the left, and you can see we get about 4 million writes and 7-ish million reads per second. And then I add my instrumentation, and you can see there's no performance overhead in doing this. There is, but it's very minor. You can't really see. And you might have noticed here, we actually got a data point out of our instrumentation that was negative. So this demonstrates that the ring buffer is in an invalid state. So that kind of clued us in on where the problem was in the ring buffer. So this is great. We can sample as data without very low performance overhead. However, this only works for low frequency events, so sampling at a low frequency. If I use the same technique to instrument every single read and write operation that the ring buffer is doing, you can see the performance overhead of that. So same performance as before. We then run the trace program, and it turns 7 million operations a second into several hundred. So this isn't suitable for doing high frequency sampling. So why is that? Well, the controller process that I have driving the debugger, that has a lot of I/O to share data between the debugger and the controller. In addition, there's a lot of overhead in jumping in and out of the kernel. There's context switches whenever you jump in and out of the kernel, so that contributes to the overhead. So is there a better way to do this? What if we could move all this user land code doing I/O and doing context switches? There's no real necessity for that to live in user land. What if we could just move all that into the kernel itself? Then you have a tracee just hitting trap instructions, jumping into the kernel. The kernel does some work to instrument the code and then jumps back into the tracee. That would be ideal. So this is actually something that a technology called BPF can accomplish for us. So what is BPF? Just real briefly, BPF is a custom instruction set that you can write in and build programs that compile to it. And it allows you to inject programs into the kernel. The kernel takes this BPF bytecode, it validates it, make sure it's safe to run, and then it'll compile it to make sure it runs fast on your native architecture. One of the things you can do with the BPF programs is you can attach various event sources to it, so we'll see that later. BPF was originally created for packet filtering, in-kernel packet filtering, so that's where it gets its name, Berkeley Packet Filter. And if you ever use TCP dump, the expression that you give TCP dump actually compiles into a BPF bytecode, so you're running a BPF program whenever you use TCP dump. So what can your BPF program do? Well, you can do a lot of things that you would expect out of a normal instruction set. One of the limitations is around memory access. You don't have full access to the kernel memory. One of the capabilities of BPF that's really important is these helper functions. So the kernel exposes a various amount of functions that can do really useful things that are useful for tracing. So reading stacks from kernel or user land, aggregating data in kernel data structures, manipulating packets. There's a whole list of capabilities that you can call into to do useful things. There's hundreds of them, so I didn't list them all here, but there's a lot of useful functionality there. So what can BPF programs not do? So your program must have finite execution. That's a big one. Like you can't go into infinite loops. You can't go into loops at all because of the probability that you might go into infinite loop. So you can't do anything that can hang the kernel. You can't acquire locks that could potentially hang the kernel. Like I mentioned before, access to memory is a little bit restricted. So yeah, there's some restrictions around what you can do with your BPF program. Just important to keep in mind. So here's kind of an example of what we want to achieve with our new program. So we have our tracee, and we have a little user space program called the tracer that it's doing a tiny bit of work in user land, but not nearly as much as previously. So what happens in this situation? Well, the tracer is going to compile our BPF program for us. It's then going to hand that off to the kernel. The kernel is going to verify and compile it. The BPF program is then going to be attached to event sources. So the tracer will tell the kernel, hey, this program I just gave you, attach these event sources to it. When those events occur, so for instance, the tracee hits a trap instruction, then the BPF program will get called and it'll handle the event. And then the program can optionally write to some in-kernel memory that then gets shared with the tracer. So I mentioned the event sources. The ones that we're going to be discussing today are uprobes primarily. There's also something called USDT probes. These are statically defined probes. On Linux, they're actually implemented using uprobes, so it's kind of using the same technology there. But yeah, there's other event sources, some kernel, dynamic and static instrumentation, networking stuff. So yeah, there's various event sources you can attach your program to. So yeah, uprobes is really awesome. It's like one of my favorite technologies. It allows you to trace any instruction in userland with a lot less overhead than ptrace. So here's an example of how uprobes works. So you have your program down at the bottom here. Each one of these blue boxes is a instruction, so variable width instruction, something like x86, 64. So in the middle here, we want to instrument the instruction in the middle. So what the kernel will do, will copy that instruction into a buffer in kernel memory called the single step out of line buffer. It'll then write a trap instruction over on top of that instruction. And then when that trap hits, the kernel will then take over, run the handler that we register with it. After the handler, our BPF code is done running, then it'll single step the one instruction out of that buffer. And then after that's done, it will then jump into the program's text just immediately after that instruction. So we were able to add this instrumentation without our program knowing. Every instruction that our program wanted to execute was able to execute. So that's uprobes. USDT I mentioned before. There are static trace points that are defined by the developer, they're defined in source code. I like to think of them as kind of like a tracing API. You're exposing these kind of landmarks that folks can then instrument later in case they are interested in debugging problems with your software. So they're really useful. You can report arbitrary data when the USDT probe fires. So they're kind of like structured logging. You can attach whatever data you want to them. But you're not paying the performance costs that you would normally pay with logging that's enabled. You only pay the performance costs when you enable these probes. There's some probes that are built into language runtimes, so Python, Node, Ruby, Java. They all have USD probes that you can either compile in or enable. And those USD probes will allow you to instrument functions and methods that are being called in those runtimes, so you can get access to language native functions. So how do we write these BPF programs? Well, there's two technologies that I've used to write these programs. The first is BCC. BCC has been around for a while, and it's really mature, has a lot of capability, but it has a little bit of a failure around complexity in writing these programs. BPF Trace, on the other hand, is very new, is released a few months ago. It exposes like a really nice language and dramatically simplifies writing these programs, but it doesn't have all the capabilities that BCC has. So I think currently there's a place for both of these tools. So BCC is the BPF Compiler Collection. So you write your BPF programs in a version of C, and BCC will compile that for you and hand it off to the kernel. It also assists with you attaching events and interacting with kernel memory. It's implemented as a shared library, so libbcc.so. There's bindings in Python Lua, and third-party Go bindings exist. So this library has a lot of really good functionality, and it's quite mature. In addition to the library, they ship a bunch of tools along with the library that are incredibly useful. I don't have time to go into them today, but I highly recommend anyone who's interested look at some of these tools. They allow you to instrument a good amount of your system, and you don't have to write a line of code. So some interesting ones are like TCP connect, TCP accept, all the TCP stuff. One that we'll see later is OpenSnoop, which just allows you to kind of snoop in on any open file system operations. So let's do a uprobe demo. So we're going to use BCC to instrument some code using uprobes. So this is the code that we want to instrument. There's no instrumentation added to this in advance. Just an infinite for loop calling a function f, and then that function is just doing an atomic increment on a counter. So the BCC code that we would write is here. So up at the top, we have a C program that's going to increment a counter in kernel memory. And then below, we just have some code that kind of wires that up to the main.f function, which is what we're interested in instrumenting. We then have a count, which we use to then read kernel memory and display that. So this is what that looks like when it runs. So we're getting around 125 million operations a second on a single thread. And then when we run our instrumentation code, you can see that drops to about 390-ish thousand operations a second. So it definitely has an overhead. uprobes are not free. But one thing to notice is when you detach from the instrumentation, you actually regain all that performance. The other thing to keep in mind is this is on a single thread, so a lot of workloads, I would venture to guess, aren't doing more than 10 to 20,000 operations a second on a single thread. If you are, then that's when you want to consider using something other than uprobes, maybe some user space instrumentation. But if you're doing less than that, then uprobes is fine to use. So that's uprobes. Let's see a demo with USDT. So we have just some Go code here that is instrumented using USDT. So the main important bits is that the function now is, instead of doing a counter, it's actually doing some work. So reaching out to Google and just doing a random search. And then when we enter the function, we fire a entry probe, and then when we exit, we fire an exit probe. So this will allow us to measure the overall latency of communicating with Google. So I'm not going to go into detail of how this works, but we basically have just two functions that keep track of the timestamps for when these events occur and correlate them and store them in a histogram. So that's the BCC program, the BPF part of it. This is the Python part, which kind of wires everything together and displays the data. It's very similar to what we saw before with uprobes. When we hit Control-C here, it just displays out the histogram. So this is that running. So on the left-hand side, you have all the queries going to Google, and then we have our instrumentation running. And when I hit Control-C here, you'll be able to see the distribution of latencies for all those requests. So yeah, that's kind of an example of using using USDT to instrument your code in advance. So all that was using BCC. So what about BPF trace? I mentioned that's like the new tool. So yeah, it dramatically simplifies writing these programs. So the counter example with uprobes that I showed before, that is on the right-hand side. And then on the left-hand side, you can see the example in BPF trace. So a lot simpler. Here's an example of doing the latency calculation and printing out a histogram. Just a handful of lines of code versus 20, 30 lines of code. So a lot less complexity. It's a lot easier to use. So to just take a step back, when I first started getting into Linux tracing, the field was like pretty messy. There was a lot of different options, a lot of different technologies to look into and investigate, a lot of different tracers. It's kind of intimidating a little bit. And I feel with BCC and BPF trace, they dramatically simplify the landscape of tools. You get all the capabilities you really want with a lot, just a few tools to use. So similar to how Docker took the kernel technologies of cgroups, namespaces, and seccomp, I feel like BPF trace has the potential to be the one tool that really exposes and makes generally usable technologies like uprobes, kprobes, BPF, trace points, etc. So yeah, we kind of got what we wanted. We are able to intercept any point of execution without restarting the process with as low overhead as possible. We're able to read it from memory and registers, collect data across multiple processes and the kernel, and we're able to do it all safely. So that's great. So how do we put this into practice? We need to deploy a container to probe our applications. So I actually put together a repo that can assist you if you want to play around with it. It's called towel, just Jason Keene /towel on GitHub. So that that's composed of a Docker image, a daemon set, and a kubectl plugin. So I'll go into what those are used for. So first, the daemon set. Some things to note about it is that it runs this container as root. So obviously, like that comes with a lot of caveats. You're running as root. It's probably something that you want to make sure you're doing correctly. Additionally, we share the host PID namespace. That's just so that we don't have to do PID mapping and enter into other PID namespaces. We also volume mount a whole bunch of stuff in order to have easy access to Docker and to have access to the file system of the containers. So this gives you a lot of power, but with great power comes great responsibility, and you have to use this wisely. So this is an example of using the towel. So I'm going to use first I'm going to get the pods just to show that Nginx is running here. And then I'm going to use the kubectl plugin towel apply just to apply the daemon set. So now that's running. So each node gets its own pod. Then I use kubectl towel exec, which will exec into the towel pod that's co-located with the same pod that I give it. So I gave it a label selector there. You can then see that it put me in the directory where the container is mounted on the host. So that's useful. I then use OpenSnoop just to snoop in on what Nginx is opening. And then every time I curl it, you can see it's hitting, or it's opening up the index.html file. So yeah, and then I use readelf here just to dump out the symbol table for Nginx. I was interested in instrumenting the request response cycle for Nginx. So yeah, I found a symbol here, HTTP process requests that look pretty interesting. So then I use BPF trace just to instrument that function, just to see if that's being invoked when I curl it. So I just say uprobe and then give it a path to Nginx and the symbol that I want to instrument. Then just print out a debug message just to show that I'm instrumenting it. So then whenever I curl it, you can see the hello KubeCon message shows up. So that's not terribly useful per se. So let's do something a little bit useful. So say I want to measure the latency of that one function, not the entire request response cycle, but I'm interested just in measuring that one function. So I have a program here that does that, just a few lines of code, and then I'm going to apply some load onto Nginx using Siege. And then whenever I control C this, you can kind of see the distribution of requests that came into that one function, not necessarily the entire request response cycle. And then afterwards, you can just use kubectl delete to clean up after yourself. You don't want these pods running in a production environment for longer than they need to be. Cool. So like I mentioned, this runs as root, so make sure to delete the daemon set when it's no longer needed. Also put the daemon set in a namespace that's restricted. So you can use just this role here. There's a resource pods exec that allows you to just control who has access to exec onto that pod. So that's useful if you want to control that. So how to get started. I have a getting started guide up in the top of the README of the Tau repo. So if you're interested in learning more, I would recommend looking at that. So yeah, with these tools, we can ask questions that we want to ask, get the answers we want, and begin to better understand our systems. That's all I got. Thank you.